Thanks so much for having me. My first time at SREcon. I'm loving it so far. So hi, I'm Chris. I live in the Boston area. I've been at Wikimedia for 5 years as an SRE. We're coming up on 5 years. Before that, I was at Google for 10 years, straddling the fuzzy line between SRE and software engineering. OK, so who's Wikimedia? What's their deal? Well, it's not just Wikipedia. It's many other projects, Wiktionary, Wikimedia Commons, which is a great image repository of freely licensed stuff, Wikivoyage, which is a great travel planning site, Wikidata, which is a big knowledge graph as triples. A lot of stuff there. There's more projects than I can put on this slide. We administer these projects. We run the infrastructure. We help the community self-organize. But the volunteer community does all the writing and the editing of all the content. We're the only nonprofit and open source project that is also a top 10 website, and that's pretty cool and fun. We also have a big emphasis on anything that is critical to our mission in the user's request path or something that we really should be doing in-house. We always pick open source solutions for it, basically whenever we can. We run all of our own bare metal in rented cages at commercial colos. We make very limited use of cloud providers, and not for anything that's in the user query path or anything that contains PII. As an org, we're very concerned about privacy, and so is basically all of our user base for various reasons. This photo is from our Dallas data center in 2015, so it's a bit dated, but still. We have about 1,800 physical servers. We have 2 core sites, both in the US, and they also each have a CDN edge on them. And then we have 4 other CDN caching-only mini sites, POPs, around the world. Here's a map. The code names here are a combination of the 2 letters for an abbreviation for the commercial provider, and then 3 letters of the nearest airport code. Our 2 core sites in the States, Ekiad and CutOffW, are running application servers, database servers, memcached, Kubernetes clusters, Ganeti VMs. They also have a CDN edge, as I said. The short story on our app servers is that they look like a classic LAMP stack. Like MediaWiki, the main application we run is a big ball of PHP that runs behind Apache, but we have Envoy on top of it and also underneath of it. So we can do TLS to outgoing things. That's really expensive in PHP. It will soon also be running on top of Kubernetes instead of on just bare metal. I'll spare you the other details, but if you're curious, you can go look. Not only is our task tracker open to the world, but so is our Grafana, all of our Git repos, from our Helm charts to our Puppet repo that manages all of our bare metal machines. From the CDN perspective, it's pretty traditional and straightforward. Each site here has its own public IP range. We do geographic-based DNS based on we look at where the resolver is coming from and try and pick the geographically closest site to then send the user to. We aren't yet doing anything fancy like Anycast, but this is straightforward, easy to understand, and it's been effective. Now I'll give you a little overview of our scale. These are just 2 graphs of the last month from our public-facing status page, which is just gets an export of a few datas out of a few metrics out of our Prometheus. Our usual daily peak is about 200,000 requests per second. Some peaks are peakier than others. As an interesting anecdote, one of the usual recurring unexpected sources of big traffic surges for us is celebrity deaths. Most recently, we weathered Queen Elizabeth's passing without any outage. The more grizzled elder SREs at Wikimedia will speak in hushed tones of the Michael Jackson effect. At the time of his passing, we were down for a few hours because all of our app servers were kind of caught in a live loop. Submitting an edit causes a cache invalidation, which means you need to do a bunch of reparsing and read-database queries and stuff like that, and they were all just doing that in a very tight loop as edits were able to be submitted. We fixed that since, and then when Kobe Bryant passed, we found a new, different bottleneck in a different part of the system, and I fixed that since, and maybe we've solved this for now. So anyway, we run a pretty well-distributed CDN. 6 sites is not bad. It's respectable. Each site has 3 independent IP transit providers. Each site is connected to at least 1 local internet peering point, usually more. That ought to be enough, right? We can abstract away the rest of the internet, treat it as a happy little cloud, and stop worrying about it. Yeah, we're all here at this conference because we know better than that, right? By the way, I hate the cloud metaphor for the internet. The only part of it that I think really stands up to any scrutiny is that if you're inside a cloud, it's quite hard to see and very easy to get lost. I think a better metaphor for the internet would be a great forest. There's many individual and varied entities, from large to small, all different. Some of them might compete, but all of them have to coexist and work together at least somewhat harmoniously. They communicate with and depend upon each other, and they form a whole that is far greater and larger than any of the individual parts. Trees, by the way, do communicate with each other. It's really cool. Of course, none of this is to say that forests are utopias. Several times a year, some subset of our users are mysteriously unable to reach our sites, getting errors like this connection timed out message. These issues are sometimes our fault, but often not. Very rarely have an obvious cause, and previously they weren't even detectable by us unless a user went out of their way to manually report that there's a problem. In very large outages, maybe we'll notice that incoming traffic levels are below what's expected, but that only happens for very large outages. It doesn't tell you anything about who's affected or where they might be. So now, I want to ask you, if a tree falls, if a user's packet gets lost in someone else's network before it gets to us, does it make a sound? Yes, it does. And it makes a sound that we can hear and get details about. Here is an illustration of an error report we might automatically receive from a user's browser when they encounter a connection timed out message like we just saw. There's a lot of useful details here. There's the URL that was fetched, the type of the error encountered, and after going through our processing pipeline, there's the user's IP address at the time, their internet service provider and country code. Now you're probably wondering, how do we get this, right? The user's web browser just told us over the internet that it can't reach us over the internet. Now, browsers will buffer these reports and send them to you later if they can't reach your reporting endpoint right away. But if you look closely, that's not what happened here. There's this age field at the top, and it's exactly what it sounds like. This report was received 0 milliseconds after the error happened. This seems magical, but it can't be, right? Well, with this spec, we rely on the fact that the internet usually works. And when things are working, we ask browsers ahead of time to remember, hey, if you have trouble talking to us in the near future, let us know at this other address. This is a simplified HTTP transaction showing this happening. There's 2 response headers that we set here. One is report to, which is part of a bigger reporting API specification that can also let you receive reports about other interesting things like content security policy violations or use of deprecated JavaScript features or JavaScript browser engine crashes. In this case, we just give it this URL a name and a time to live in the browser. And then there is this NEL header, network error logging. Again, a TTL referencing the name of the reporting endpoint. And then 2 other fields, a failure fraction and a success fraction. Those are exactly what they sound like. We're saying on failures, please send us a request 5%, 1/20th of the time. And on successes, that's great. That's fine. All of this is defined in a draft spec published by the W3C, is currently shipped and enabled with Chrome, Opera, and other Chromium derivatives, like Microsoft Edge. Firefox and Safari don't support NEL, mostly because of potential privacy concerns. There are some potential super cookie-like things you could do with NEL theoretically, and it's a little hard to reason about, so they're scared of it, which I think is fine. But for us, about half of our global user base uses a browser that ships with this enabled. So this is great. We get free network telemetry from half of our users, right? Now, there are some caveats. First of all, we set that 5% sampling rate. We don't want to receive every error report, and as I'll get into later, there's a lot that are unfixable or working as intended or just noise. And as for the eventually part, they will buffer. Browsers will buffer these and send them to you later aggregated. But we have a neat trick to avoid doing that. One thing that you can do is just run collectors off your own infrastructure. But another thing that you can do is just try to reduce the amount of fate sharing that you have between your usual best path to your CDN and where the nels go. That's a lot less latency sensitive. It's a background upload, so you don't care about direct user path stuff that much. So we maintain our own open source authoritative name server called GDNSD. Amongst other things, it supports geographic DNS. And we added a feature that you can just set it on one of the host names and have it return the second best zone instead of the first best zone. We turn that on just for the domain that this intake logging.wikimedia domain that we receive these reports on. In practice, this works great. This is a histogram of the report age over the last week as of last night for the reports that we think indicate connectivity trouble. And the vast majority of them are under 10 minutes, like almost all of them, and most of them are within 1 minute. All right, so that's a neat trick, but let's backtrack a little bit and talk about the overall architecture here. To represent the end user, we have my two cats who are glaring at us expectantly, either because they can't access Wikipedia or because they feel like that their mean time between Treatos SLO has been unjustly violated. The spec just asks that browsers send a JSON blob of a particular structure and post it to an endpoint. We actually already had a component that our data engineering team had built that knew how to receive HTTP posts with a user-specified JSON schema and then post it to Kafka. So I made 1 or 2 changes to that around CORS stuff and something else, like one-line patches, and it just worked. So we started working on this in July 2020. We turned it on for first a few domains and then all of our domains in September 2020. In 2021 early, I went back and added actually tagging IP geolocation of the uploaded user address, which was really useful for tracking down localized outages. And then in October 2021, we started paging on this. It's caught issues that we wouldn't have otherwise. And there really haven't been that many false positives. There were some that weren't actionable, like a really large ISP has a totally widespread outage and can't get traffic almost anywhere. That paged us, but it's hard to differentiate that from a really large or a few really large ISPs are having trouble talking to just you and you have to do something about it. OK, so now a little more detail on the spec and the report bodies themselves. They have all the basic metadata of an HTTP request that you would expect. You know, the URL, a GET, the protocol, et cetera. They also have a few other really nice metadata fields. Elapsed time, which is exactly what it sounds like, just the number of milliseconds from when the user started doing the thing in their browser to when the report was generated because either it worked or the browser gave up. Age, how many milliseconds old it was at the time that the report was submitted. The sampling fraction at generation time, which you can use to reason about if you do anything dynamic there. There's a few other things in there. There's the response code, if any, in the cases where the phase was one of DNS or connection, and the type here was one of those where it didn't make it to the HTTP step. That'll be nothing. Phase, DNS connection application. And type has, like, I don't know, 30 different values. It's just a big enum, and I treat it as a string. DNS name not resolved, pretty obvious. TCP timed out. Your SYN handshake timed out. TLS cert date invalid. And HTTP response redirect loop, few examples, pretty self-explanatory. Type is the single most important field in any report. It gives you a lot of good data, and it's the one field to pull signal out of the noise here. So let's talk about that a little more. Highest signal, TCP timed out and TCP address unreachable have empirically been really good signal for us of when something is grossly wrong with our networks or the internet or both. Those are the two that we paged on. I picked a threshold. I'm not a statistician. I'm more of a digital plumber. So I looked at the last 6 months and picked something that wouldn't have paged except the one time that it should have, and that has been fine since. We don't page on DNS name not resolved right now because usually if something is so broken that that doesn't work, we won't get nels in the first place in a timely manner. And usually also in that case, we're also still getting the first two. So that's been fine. It's still good signal, though. It's worth putting on your graphs. There's some that are noisy. So TCP reset, TCP closed, H2 ping failed. You'll see all of these from just random stuff. Someone was using a page, or someone was on their phone looking up something, walks outside, they're off their Wi-Fi, and they're on a cell network. Well, that's going to produce one of those events the next time they pull their phone out of their pocket again, probably. Ping failed, similarly, an HTTP2 persistent connection just timed out or went away for some reason. You know, it could be anything from that same thing to someone stopped using their device, and when they came back, their router had timed out that entering in its contract table or something. We display those. We don't worry about them. They're useful mostly when they're associated with a lot of other events that are a lot of other types of events that are more important. Abandoned right here is just literally users click the stop or back button or close the tab before the page load had finished. Those are, again, interesting if you see them in large volumes, but also happen all the time. In practice, we mostly ignore these aside from plotting them. Then there's ones that are just noise. HTTP.error, yeah, you will get a 404 HTTP.error report for everything that shows up in your own actual request analytics pipeline for people hot linking stuff that's not there anymore or whatever, right? Unknown, there's a grab bag, like it's literally the default in the case statement in the Chromium network implementation. I've never dug into what it actually is, but we just ignore them. They are ingested, but I've never looked at them in depth because everything else has worked fine. Okay, so what's not in a network error logging report? Client IP address. You have to record that at the time of ingestion yourself. And also, there's no indication of whether that's changed between the time of the report being generated from a bad request and you actually receiving it. You can kind of guess based on the age field, but it's still a guess. And going with that, any information that's derived from the IP address, like I showed you AS number before, we add that in our traffic stack, right? There's also no absolute timestamps in here, none. And this surprised me at first, but it's actually really clever. So it sidesteps you having to reason about clock skew, and it also makes it impossible for you to reason about clock skew, and that eliminates a fingerprinting risk where you could potentially use this to de-anonymize users based on their own clock skew. I wouldn't have thought of that. I saw it in the spec, and I thought that was really cool, and it's clever design that I wanted to point out in this context. So now we're going to quickly walk through a few case studies of incidents where NEL was uniquely helpful, either in detection or diagnosis or fix or verification of fix. The first one, we have a service, a microservice that lets people download PDF, like rendered PDFs of wiki articles. We started getting a bunch of user reports that they were getting corrupted PDFs. All of our metrics looks fine. We couldn't reproduce it doing things internally from production. And if you looked at all of the CDN nodes across all of the sites, it was wildly inconsistent when this happened and didn't. The same PDF would sometimes work, sometimes not. There was just no obvious connection in time or space. And at its worst, it looked like this was happening to 20% of uploads based on our estimates of polling the CDN edge. That's heinous, and yet we have no signal on this, aside from user reports. This also began just after we migrated that service, which is basically Node.js wrapping Chromium, headless Chromium, and then dumping the PDF out, had moved off of bare metal and onto our Kubernetes cluster. So there was a lot of suspicion around, well, clearly that's involved. That turned out to not be the case. But it took a while to track that down. The corruption was actually truncation, so users were getting an incomplete file. And then we started thinking about, once we figured that out, we started thinking about, okay, there's literally 6 different implementations of HTTP as reverse proxies between this Node.js thing and where the users sit. Also, the Node.js thing emits using chunked encoding, and some things care about content length. It's a huge mess. It's like an onion. There's a lot of layers and sometimes a lot of crying. So it turned out to be our CDN is actually HA proxy for TLS termination, and then Varnish to do a bunch of business logic and in-memory caching, and then behind it, Apache traffic server to do on-disk caching and TLS with the backend services, and routing of requests to different backend services. There's something in Varnish called nuke limit, which I'm going to get this wrong, so forgive me, but it's effectively in the hot path how many objects it's willing to evict from the cache to make space for a new big thing in its ephemeral storage. It's the kind of knob where if you have wildly varying object sizes, let's say your CDN node is serving both 16 kilobyte PNG map tiles and 50 megabyte PDFs, there's no good setting for this number. It's just not a great model of that usage. And of course, encountering this error or not mid-download depends on the state of the cache server and which data center you landed on and which machine in that data center that you landed on, the current load and hit rate, phase of the moon, et cetera. There's the full story on our bug tracker there. There's a link. It'll be in the references later, too. But anyway, we had kind of just started using Nels at the time. And it's like, all right, I know the URL path of that, and I apologize for the Elasticsearch syntax that's up top. And I'm just going to look for content length mismatch, which is the report type that matches up with this error, since I control F'd for length in the RFC and found that. And what do you know? One of our Varnish wizards deployed this nuke limit change, and then instead of getting a few errors an hour, we had none for 8 hours. And that was really nice, right? This was a bug that was really hard to track down. It was a few days of work off and on with people reaching out back to users, are you still seeing this? But we had a clear signal instead. All right, let's look at another issue, this around detection. So I referenced that we have this pretty redundant CDN where each site also has 3 independent transit providers. Sometimes, despite buying IP transit from 3 providers at one site and even making sure that their fibers enter on different physical sides of the building, it turns out that they all depend on one single underground fiber conduit somewhere between them and the rest of the San Francisco Bay Area. And then you get updates like this from all 3 of them for the next few hours afterwards, which are really just kind of depressing and made me feel bad for the people doing this work in terms of digging out concrete and slurry to get into this conduit, where then it turns out there's no room. And yeah, there's 5 to 6 other contractors in the area. No estimated time to repair at this time. So this resulted in, as soon as the drill bit hit, the site appearing offline to the rest of the world. Mysteriously, we still kept our BGP sessions with our transit providers there, which, anyway. We had user reports we had a few user reports within a few minutes, but we had incoming Nel reports within seconds of this happening at about 23:30. We also had an especially high volume of Nel reports, which was notable because we could immediately tell that, no, this isn't just an isolated thing. This isn't 1 or 2 people have a wacky ISP. This is the whole San Francisco site is down. Take it out of DNS now. We also, have a none paging alert for a traffic drop, right? As compared to 30 minutes ago or to last week at this time, you're seeing a lot fewer requests than you expect to be seeing. But usually when that fires, it's because some bulk scraper just finished its cron job for the afternoon, and everyone ignores it. All right, final case study here. So we make use of a few different providers of DDoS scrubbing services, only at layer 3 and 4, basically. Stuff like, oh, it's pretty unusual that they're getting half a terabit of UDP traffic. Let's not forward that on to them. So we turned it on with a newer provider, or actually with a trusted provider who had just upgraded some of their data centers, but we didn't know that yet. And we started seeing issues just for Italy. This is unfortunately before I had actually done the GeoIP stuff, and this was a major motivation for fixing that. But this is what I like to call a, well, there's your problem kind of graph. The start of that square wave function is when we turned it on, and the end of it is when we turned it off and said, hey, we think this is broken, can you please investigate? This is one plot from a few hours on one day of what was something that was back and forth for many, many months. And without Nell, our vendor wouldn't have believed us. All of their data that they had looked like stuff was fine. It was the reason why they took us seriously. And long, long after this, we got a fun postmortem, which unfortunately omitted a bunch of the best details. But it was something about a new hardware design for their own sites, something about link aggregation plus equal cost multipath, and a lot of back and forth between them and their router hardware vendors. So yeah. I do want to point out something here. You'll notice at the end of it, there is at the very end, it spikes to higher than it was, and then tapers off, and then there's exponential back off, what looks like exponential back off with jitter happening afterwards, right? Like there's this long tail of reports coming in that are old, because the long spike at the end is actually when the outage stopped, and it's from users who had their connectivity broken so badly by being hashed onto whatever bad link here just randomly that they couldn't access not just the closest site, but any of them. And then the long tail similarly. And I found this little gem in the original specification describing like, oh, like there's an issue, there's a potential risk of thundering herd here. Employ some sort of exponential backoff algorithm, which increases the retry period with the number of failures, and it adds some random jitter. And let's use the reference of last resort if we can find a good description of how to do this as an algorithm. All right, a few closing thoughts. So we have a few plans for extending this at Wikimedia, not just paging on it based when we think that users are affected. One is that we have some vague ideas, which we haven't refined yet, and I hope to get back to you soon, about using Nels as a way to help write and measure an end-to-end user, like direct end-user SLO for our CDN. That's in the idea stage. It's not even experimental yet. The second one, the idea of using this as part of an implementation of doing latency mapping based on IP spaces to the closest data center to us, we're starting to experiment with now. And the basic sketch of the idea is you make a per site domain name for each of your CDN edges. You set success fraction in Nell to 1.0. You probabilistically trigger some fetches in JavaScript, some fraction of the time for some % of users TBD. And then you don't even look at the results, because the browser is going to give you an elapsed time and a status report and upload that in the background for you. And you can just look at the data afterwards. There's off-the-shelf ways to do this right now. There is at least one CDN provider, it's Cloudflare, but I don't write that on the side, who you can just go into the dashboard and click Enable Nell, and they're already terminating layer 7 for you. You will just get the HTTP response headers emitted by them and pointing to their own aggregation infrastructure. There's others, kind of external monitoring providers, people like Catchpoint, Report URI, a few others that have collectors ready for you to use, and you just have to set the response headers in your application. This is not an endorsement of any of them. I have no experience with these products, but wanted to mention it for awareness. And also, doing it yourself isn't that hard. There's concerns, but if you're already running a CDN, this is not hard, right? And it's been really useful for us. There are caveats. One, you're persisting objects in the browsers of your users, potentially long-lived objects. And you can create opportunities for cascading failure this way, despite exponential backoff and such like that. Reports also can be recursive. In the report to and Nell response headers, that applies to any traffic to that domain. And you can just emit those on your report receiver also, if that's not a special domain or if it is. That can be good, that can be bad. It depends on your use case and what you want to care about. And also be prepared for a lot of background noise. People wander off and on of networks, out of cellular service range and back in. People encounter captive portals. NAT contracting tables expire. There's momentary blips all the time. We've seen stuff that looks like either DNS resolver bugs or memory corruption happening somewhere between the resolver and the user, where we're getting reports for like domains that have no relation to us, but they happen to hit us once in the past, and we get it again later. And yeah, the good news about end-to-end observability is you're getting to see what actually happens in the real world. And the bad news is sometimes that's bewildering. Don't get lost. Either way, it's not hard to set up. It gives you actual end-to-end observability. And even if you're just using someone else's CDN, I would just ask them, like, why don't you offer this? Because honestly, you're doing them a favor, because I'm sure that their traffic team is spending a lot of time tracking down stuff like this that this would help with. Anyway, thanks so much. I'm Chris.